Hi guys, can you guys hear me?
Yes, Dr. Lee.
Okay. All right. So I'm going to continue where we left off last week. Um, Last week we've learned about how to balance the redox reaction in acidic solution, and today we're going to learn how to balance redox reaction in basic solution. Okay, so again, the steps are very similar. You will follow those steps that you use to balance the redox reaction in acidic solution, and then the later there's going to be a little bit additional steps involved in balancing a basic solution. Okay, reaction in basic solution. So the key point is that after balancing the reaction equation as if treated as if you're balancing a acidic redox reaction, and then once the equation is balanced, you should add hydroxide. Okay, you should hydroxide to each side to neutralize any proton present in the equation, and then proton and hydroxide, you write it as water. Okay, let's try a sample exercise. So complete the balance equation for a redox reaction that takes place in basic solution. Okay, so we have basic solution here. The very first step, since the very first step is to write a half reaction, we need to figure out which substance got oxidized and reduced. Okay, so if we assign the oxidation numbers for cyanide, you have the oxidation number change from -1 to +1. For manganese, the oxidation number changed from +7 to +4. Okay, so we know that the oxidation half reaction is this portion. Reduction half reaction is this portion. Okay, I'm going to write that down. Oxidation half reaction is this portion, aqueous. Then the reduction half reaction is MnO4 being reduced to MnO2. Okay. If we balanced each half reactions according to the previous steps that we learned, treat it as if it was an acidic condition, the balanced oxidation reaction is going to look something like this. Balanced oxidation half reaction is going to be this is the balanced oxidation half reaction. The balanced reduction half reaction is going to look something like this. Okay. then for the redox reaction in basic condition, we need some additional step after this. Okay, so for if it was an acidic solution, you just have to balance the charge using the electrons, add up both oxidation reduction reaction, and you're done. But before balancing the charge using electrons, for basic solution, reaction in basic solution, you need additional step from here. Okay, so what you have to do is you will have to add hydroxide to both sides to neutralize any proton present in the system. Okay, so as you can see, you have 2 protons here. You have 4 protons here. You're going to add hydroxide to balance out these protons. Okay, so because you have 2 protons, you're going to add 2 hydroxide. Okay, and then you are going to add 2 hydroxide on this side as well. Okay, for here you have 4 protons, so in order to balance out this, you're going to add 4 of the hydroxide. You also add 4 hydroxide on this side. Okay. And then the next step is writing out the neutralized outcome between proton and the hydroxide. Okay. So this proton and this hydroxide will create 2 water. This proton and this hydroxide will create 4 water molecule. Okay. So then we have 2OH plus cyanide plus water, CNO minus plus aqueous. 2 proton and 2 hydroxide will form 2 water, and then 2 electrons. For the reduction part, you have 4 water from this and this, 3 electrons, MnO4, 2 minus, MnO2 solid, plus 2 water, plus 4 hydroxide. Okay, and then the next step is canceling out waters that appear on both sides. So as you can see, for the oxidation part, you have 1 water here, 2 water here, so you'll be left with 1 water. Okay, and then for here you have 2 waters here, 4 waters here, so you're going to be left with 2 water. Okay, and then after that, the final step is to balance the charges of both half reactions by having equal numbers of electrons lost and gained during the redox reaction. Okay, so just going to have 1 water. We're just going to have 2 water here. This water goes away. Okay, so since the oxidation half reaction has lost 2 electrons, if we multiply If we multiply 3 to the entire equation, we have lost 6 electrons in the oxidation part. Okay, and then since reduction half reaction gained 3 electrons, okay, if we multiply 2 to the entire equation, we will be gaining 6 electrons. Okay, then the electrons lost and gained during the oxidation Sorry, guys. Can you guys hear me? And can you guys see the screen that I'm sharing right now?
Yes.
Okay, so where did I stop? Sorry. Can somebody tell me where I stopped? I think I was just talking to myself. I thought everyone was listening to me. Did I go?
It's like just before you copied that second reaction.
Here, copy just before I copy this part?
Yeah, right after you got the phone call.
Okay. So everyone got that the 6 electron part, right? So multiply by 3, multiply by 2. Did everyone get this part?
Yes.
Okay. All right. So I'm just going to change the coefficients. Okay. Now that we're multiplying 3 to the entire oxidation half reaction, it's going to be 6, 3, 3, 3, 6. Okay, and since we're multiplying 2 to the entire reduction reaction, it's going to be 4, 6, 2, 2, and then 8. All right, so the final step is adding up 2 half reactions. Okay, so after adding up, we have 3 cyanide, it's 2 hydroxide. Okay, this is going to be the final balanced redox reaction in basic solution. Okay, so six electrons appear on both sides, the amount of electron lost and gained during this reaction. So we're just going to eliminate that, and this is the final balanced redox reaction in basic solution. Let me know if anyone needs more time on this slide.
Yes.
So you need more time?
Yeah, just like 10 seconds.
Okay. Let me know when you're done.
Thank you.
Okay. All right, so now that we have pretty good understanding of redox reaction and how to balance redox reactions in acidic and basic condition, we will move on to learn about how chemical reactions can create electricity. Okay? So we will learn how chemical reactions can produce electricity through transfer of electrons. So the key idea is that through the energy released from a spontaneous redox reaction. So spontaneous redox reaction um, will have electron transfer, and the energy released from this reaction is used to perform electrical work. Okay, the electrochemical cell where spontaneous redox reaction produce electricity is called voltaic cell. Okay, or also called galvanic cell. Okay, they're the same. They mean for the convenience, I'll just call it voltaic cells throughout this chapter, but they refer to the same thing. Okay, so as you can see from this diagram over here, spontaneous redox reaction between copper and zinc is producing electric current. And we're going to take a look into the detail what chemical reaction is occurring in this voltaic cell. So this is the voltaic cell. Okay, I have correct diagram over here. All right, so this is the voltaic cell. The beaker on the left here, this solution contains zinc sulfate aqueous solution. Okay. This solution contains zinc sulfate aqueous solution. Okay, so you have zinc 2 plus, SO4 2 minus floating around in the system. Okay, floating around the system. The beaker on the beaker on the right contains copper sulfate solution. Okay, so you have copper ion and sulfate ion floating around in the water. Okay, in the beaker on the left, there is also a piece of zinc over here. Okay, a piece of zinc metal sticking to the aqueous solution. The beaker on the right also has a piece of copper metal submerged into the aqueous solution. Okay, so piece of zinc here we have zinc. Here we have copper. Okay, and these two pieces of metal is connected by a metal wire. Then electrons spontaneously start to move due to the spontaneous redox reaction between zinc and copper. And these moving electrons from zinc to copper generate electricity in voltaic cells. So if we have a voltmeter, it can actually measure how much electricity it's generating. And if we stick a light bulb in here, the light bulb will lit up, okay? It will turn on. So among 4 substances contained in two beakers, you have zinc and zinc 2+ in left beaker. You have copper 2+ and copper in the right beaker. Okay, because copper 2+ is more greedier for electrons. When zinc and copper 2+ they fight for electrons, copper 2+ wins the electron war. Okay, copper 2+ steals electrons from zinc metal. Okay, so what happens when copper 2+ steals electrons from the zinc metal? The zinc metal will lose electrons and will be oxidized. So then, because zinc, let's say this piece of zinc lost its electrons, it's going to be oxidized and it will become zinc 2+. Okay, and then what happens to this zinc 2+? This zinc 2+ will be dissolved in this medium aqueous solution because it's in ionic form. So note that neutral atom, see zinc over here, copper over here, these are neutral atoms. Neutral atoms can make up solid metal, but metal ions that are in ionic form will typically dissolve in water. I'm going to write that down.
Dr. Lee,
Yes?
how do we know that copper wins the electron war? I'm just a little fuzzy on that part.
So we will talk about that in a little bit. I will show you a table and explain why copper has, but it's a natural tendency. It's like a natural tendency of copper to have more desire for electrons. Do you remember electronegativity from Gen Chem 1?
Yes, I do.
Yes, so those are its natural copper's instinct. Okay, so those are their natural characteristic. But soon, in few slides later, I will show you a table, clearly explain the order, which one has higher desire for electrons. Okay, I'll show you in a little bit. But for now, I'm just going to explain to you how this voltaic cell is working. Okay, so neutral atoms make up solid metal. But metal ions in ionic form will dissolve in water. Okay, so these zinc metals, okay, when they're in neutral form, they make up a piece of metal, but then after they become oxidized, it will become zinc 2+. It will be dissolved in water, and then this metal will lose a little bit chunk of zinc. Okay, let's look at so as time goes by, zinc solid will slowly become a zinc 2+ ion. So this will become zinc 2+ ion. This will become zinc 2+ ions, and zinc solid will lose its mass along the time. Okay. Let's take a look at the right beaker, the beaker with copper. So what happens is the copper 2+ that's floating around in the system, it will come close to this copper metal over here. Okay, it will come close to copper metal and eat up the electron passed from the zinc side. Okay, so the electrons were traveling down here. Okay, and then this copper 2+ will swallow those electrons. Okay, and where did those electrons come from? Those electrons come from here. Okay, so after copper 2 plus gains electrons, it is now in reduced form, right? So then copper 2 plus will become copper. It will become neutral metal. It will become copper. Okay, and then as time goes by, more and more copper 2 plus floating around in the beaker will become copper, become neutral atom, and then it will deposit into this copper metal piece. So as time goes by, this piece of copper metal will gain mass over time. Why? Because copper 2 plus are becoming neutral atom over time due to the reduction. Okay, so the site where oxidation occurs, this is called anode. Okay, this is an oxidation site. The site where reduction occurs is called cathode. Okay, so since oxidation occurs on the left beaker, left side is the oxidation site. The oxidation process is specifically occurring on the zinc metal surface. So we call zinc metal, this piece of exact piece of zinc metal is called anode. Okay, and this copper piece of metal is called the cathode. Okay, so since oxidation is occurring on the left side of the beaker, the left beaker voltaic cell is called oxidation half cell. Okay.
Professor?
Yeah.
So when the electrons from the anode are being taken into the other substance, what exactly is it taking over? Like, I know it's an electron, but is it zinc or is it SO4?
Where the electron is lost? Zinc.
So then,
this piece of zinc is losing 2 electrons. And then if it becomes oxidized and it falls off from the piece of metal, and now you have additional zinc 2 plus floating around in the system.
and that's why when it travels through the wire, it will neutralize copper.
And then these electrons that's traveling through this wire, it's going to arrive at the cathode. And who's going to receive that electron? These copper 2 plus that's been floating around in the beaker, they will come close to this copper metal and then will receive those 2 electrons, eat up those 2 electrons, pass through this wire. Does that make sense?
It does. What happens to the SO4 in both solutions?
I will explain to you in a little bit.
Okay, and then also, could I look at the red part for a second? The red note you made?
Here?
Yeah.
Yeah. Okay, so this left beaker is called oxidation half cell. This right beaker is called reduction half cell. Okay. So the last thing we need to talk about from this diagram over here, are you done with this? Let me
I
know when
am,
you're
thank
done.
you.
Oh, you're done? Okay. So the last thing we need to talk about from this diagram is the salt bridge over here. Okay, salt bridge. So there's a salt bridge. Salt bridge that looks like this. Why do we need a salt bridge? For a voltaic cell, a salt bridge containing salt solutions such as sodium nitrate, sodium sulfate. So here they use the sodium nitrate. Sodium nitrate salt bridge. Okay, so for a voltaic cell, a salt bridge containing salt solutions such as sodium nitrate, or it can be sodium sulfate, etc., is inserted connecting both cells. Okay, so there are some paste or gel or cotton blocking the electrolyte solution from electrolyte solution. So this salt solution is not poured into these half cells. Okay, so it's like a gel or paste or cotton and temporarily blocked. So the purpose of salt bridge is to neutralize the built up ions in both beakers. So which ions are getting built up? Somebody asked earlier what happens to the sulfate, right? So if you look at the left beaker, due to the continuous oxidation, more and more zinc 2 positive will get built up. Then in order to balance this, you have more cation concentration than the anion in this medium due to the continuous production of zinc 2 plus. So due to the build-up of this cation, what happens is this nitrate anion will slowly move towards the tip of the bridge and move into the beaker to balance out any zinc 2 plus that have been built up. So this nitrate, okay, it will smear into through this cotton, and then it will go try to neutralize the zinc 2 plus that has been that's been building up. Okay, if you look at the right side of the beaker, due to the continuous reduction, you will have less and less of the copper 2 plus as time goes by, and you will have this sulfate getting built up. Okay, so now in this system, you have more anion concentration versus cation concentration. Okay, so in order to relieve that anion's concentration, what's going to happen is that this cation of the salt, the sodium cation, will slowly move towards the tip of the bridge and move into the beaker and balance out any sulfate that has been built up. Okay, so on your exam, if this diagram is given, oh, by the way, okay, yeah, so on your exam, if this diagram is given without any label, you should be able to identify where the anode is, where the cathode is. You should be able to point out the site of the oxidation, site of the reduction, the direction of the electron flow. Okay, you should be able to answer any questions that relates to this diagram. And don't forget to study the purpose of the salt bridge also. The key point is that electrons will always flow from anode to cathode. Okay. All right. And here is the. Oh yeah. Okay. I know what happened. So I accidentally put wrong diagram on the slide. Okay. So anybody's having this diagram, you need to replace with this diagram. So this this new PowerPoint will be uploaded after I finish this chapter, so you can use my diagram, or I can post this diagram separately on Web Campus just so you can insert it into your own PDF file if you don't want to use my note. Okay, so I will upload that diagram sometime today and then make a note. Slide 27, chapter 20. Okay, I put a wrong diagram originally. This is the correct diagram. All right, and here is a general diagram of any voltaic cell. Okay, so the electrons move from anode. Electrons move from anode to cathode, and when electrons reach cathode, the cations swimming in the right side of the half cell, okay, cations swimming in the right side in the half cell will attach to the cathode and receive the electrons that have been flown into the cathode. Okay, the left half cell contains So for the specific example, we had copper and sulfate, right? So this cation will, that's been swimming in this medium in right side of the half cell, will attach to the cathode, and then receive these electrons that have been passed down, passed from the left side of the half cell. The left half cell, let's say you contained zinc and sulfate. Okay, you have zinc 2 plus and sulfate 2 minus floating around. Oxidation in the anode, oxidation of the zinc metal, right? Oxidation of piece of zinc metal will generate more and more zinc 2 plus. Okay, concentration of zinc 2 plus and sulfate, the sulfate is shifted. Okay, we now have a lot more zinc 2 plus in the left beaker. The right half cell contains, due to the reduction, more and more sulfate is going to get left behind. Okay, due to copper 2 plus participating in this receiving electron, the reduction part. Okay, so due to this, as time goes by, the zinc metal will lose its mass because it's transforming into zinc ion. As time goes by, copper will gain its mass because more and more copper 2 plus is receiving electron and becoming copper metal. Okay, and then again, salt bridge, sometimes it doesn't have to be the U shape, it can be like a barrier. Okay, so what happens in the salt bridge is that the cations of the salt, okay, the cations of the salt is going to move to the cathode to balance out any building up anions in this beaker. Anions of the in the salt bridge, okay, will move towards the anode side, okay, to balance out any cations that have been building up. Okay, so here's a trick to remember direction of the ion flow in the salt bridge. Okay, for salt bridge, cations in salt bridge move towards cathode half cell. Okay, anions in salt bridge move towards anode. Okay, so cation, for example, sodium NO3. The example for anions is going to be NO3. Okay, so here's an easy way to remember direction of the ions flow in the salt bridge. So again, this continuous flow of the electron, okay, creates electricity, which can be detected by the voltmeter. And when you study for the voltaic cell, make sure you are able to draw this voltaic cell diagram from the scratch. Okay, although there's no free response question on the exam, if you are not able to draw this from scratch, if there's absolutely no label, and I ask you to label these through multiple choice questions, you're not going to be able to actually label it. Okay, it is not that difficult, but it is quite confusing. So I highly recommend you guys try to draw out this voltaic cell diagram from the scratch. Okay, you will have multiple questions on the exam related to this voltaic cell. Okay, so let's try a sample exercise. You are given an oxidation reduction reaction. Okay, the question says this redox reaction is somewhat spontaneous. Solution containing potassium dichromate and sulfuric acid is poured into one beaker. Solution of potassium iodide is poured into another beaker. A salt bridge is used to join the beakers. Okay. A metallic conductor that will not react with either solution, such as platinum foil, is suspended in each solution. The two conductors are connected with wires through a voltmeter, or some other device to detect an electric current. The resulting voltaic cell generates an electric current. Indicate the reaction occurring at the anode, the reaction occurring at the cathode. The direction of electron migration, direction of ion migration, signs of the electrodes. So we are given a spontaneous redox reaction under acidic condition, okay? And are asked to determine resulting voltaic cells reaction occurring at the anode, at the cathode, direction of electron, direction of ion migration, and signs of the electrodes. In order to determine these information, it's always easier to draw out the voltaic cells diagram. So I drew it beforehand, so it's easier for us to visualize the voltaic cell. This reaction is actually very similar to the redox reaction that we encountered in sample exercise. (20.2). In sample exercise 20.2, we used chloride instead of iodide. Okay, that was the only difference. The coefficients are exactly the same. Everything is pretty much similar. Okay, so in the previous sample exercise, we have already figured out the reduction half reaction, oxidation half reaction for this redox reaction involving dichromate. Okay, so figuring out the reduction half reaction, oxidation half reaction for this reaction shouldn't be too difficult. I am not going to go over that part because I'm running out of time. If you can, try to figure out the oxidation and reduction half reactions by yourself. And again, you can always get the help from sample exercise 20.2. Okay, so the reduction half reaction is this. Okay, the oxidation half reaction is this. Okay, from this diagram, if the left cell is anode, oxidation occurs here. Okay, so the reaction occur in this cell is going to be this oxidation reaction. If we put potassium iodide in this cell, okay, let's say potassium iodide is in one cell, these two in other cell, right? If we put potassium iodide in this cell, there will be potassium and iodide ions floating around, and the iodide will spontaneously lose 6 electrons and becomes iodine solid. Okay, this is solid. Okay, so among these two floating around in the system, this will spontaneously lose 6 electrons and become iodine solid. If the right cell is cathode, reduction will occur here. So the reaction occurring in this cell is going to be this reduction reaction. Okay, so in this cell, what happens is if we put potassium dichromate and sulfuric acid, the potassium and dichromate ions will be floating around in the cell. The dichromate will come close to this reaction site. It will spontaneously gain that 6 electrons that have been transferred from the other cell. Okay, so the dichromate will gain 6 electrons and will become chromate, chromium ion. Okay, chromium ion. The special feature about this cell is that the anode and cathode itself is not iodine and dichromate itself. Okay, remember the voltaic cell that we observed before, it was zinc metal, copper metal itself, but here this is not iodine, this is not dichromate. Okay, this is just a piece of metal such as platinum, that does not participate in the reaction but merely provides a surface area for the oxidation and reduction reactions can happen. Okay, so it's like a plate. Okay, so platinum metal will not participate in the reaction. It just provides a medium, a surface area, so that these electrons can be transferred. Okay, so when we and then that's that. And as for the salt bridge, the anion of the salt bridge will smear into where the anode is. The anion goes to the direction of the anode. Okay, so the anion is going to go to the anode and try to balance out any potassium that's getting built up. The cation in the salt bridge will smear into where the cathode is, and it will try to balance out any anion that's been building up. Okay. Sorry, the cation in the salt bridge will smear into where the cathode is, and it will try to balance out any cation, any anion that's building up within this right half cell. Okay. So that's that for voltaic cell. And did I explain everything? Reaction at the anode, reaction at the cathode, direction of the electron migration. So electron will migrate from anode to cathode. Direction of ion migration, the ion, so we're going to the anion of the salt bridge is going to migrate towards the anode. Cation of the salt bridge will migrate towards the cathode. Signs of the electrodes: anode is always negative, cathode is always positive. Okay. So what causes this spontaneous transfer of electrons? Somebody just asked earlier. Just as water flows spontaneously one way in the waterfall, electrons also flow spontaneously from one direction to another direction. So it's like a spontaneous flow. It's just natural instinct, natural characteristics. Electrons spontaneously travel from anode to cathode, okay, due to the difference in potential energy difference, okay. Electrons flow spontaneously towards the electrode with more positive electrical potential, okay. And the potential difference between two electrodes of voltaic cell is called cell potential. And oops, or it's labeled E cell. And because this potential, I'm going to write that down. Potential difference between two electrodes of voltaic cell. Okay. And because this potential difference, it provides driving force that pushes electrons through the external circuit. Pushes the electrons through this external circuit. This force is also called electromotive. This force is called electromotive force. The driving force. This potential difference provides driving force that pushes electrons through external circuit. Okay, this force is electromotive force, or EMF. Okay, electromotive force is basically a force to push the electrons through the conductor. Okay, force to push the electrons through the conductor. It's a force. Okay. The cell potential, and cell potential in EMF, they refer to the same thing. The cell potential, or EMF, is measured in volts. Okay, and you need to know this unit conversion. 1 volt equal to 1 joule per coulomb. Okay. And the cell potential measured under standard condition is called standard cell potential. Okay, so the standard cell potential is cell potential measured under standard condition, and it is labeled like this. Okay, again, what's a standard condition? Standard conditions are 1 molar, 1 atmospheric pressure, 25 degrees Celsius. So the standard cell potential of a voltaic cell depends on what's on the cathode and what's on the anode. Depends on what you have on the cathode and anode. Of course, the cell potential is going to be different every time. Okay, so a different combination of cathode and anode will generate different cell potentials. In order to measure the cell potential of different combinations of substances at the cathode and anode, a standard reduction potentials are pre-measured for a lot of substances. Okay, standard reduction potentials are measured. The standard reduction potential is measure of how much a substance is willing to go through reduction. How much a substance is willing to accept electron. How much a substance is greedy for electron. How much a substance is hungry for electron. Okay, how likely a species will gain electron. That's the reduction potential. Okay, I'm going to write that down. Measure of how much a substance is willing to go through reduction or accept electrons. Okay. So here are the pre-measured reduction potentials of various substances. Okay, so the standard reduction potential is denoted as E naught, and this RED stands for reduction. Okay, so let's say standard reduction potential of positive 2.87, basically so among these, more positive values, more positive standard reduction potential value means these are more as you go up the table, as the positive standard reduction values gets more positive, higher reduction potential. That tells us that the substance is more likely to be reduced, more likely to going to be reduced, more likely to go through reduction, more hungry for electron. So if you look at here, copper here, zinc down here. So according to this table, which one between copper and zinc, which one has more higher reduction potential? Copper, it has higher reduction potential. Copper has higher potential to become reduced. That's why during the zinc and copper voltaic cell, electron flew spontaneously from zinc to copper because copper 2+ has higher potential to become reduced compared to the zinc. Okay.
Do you have to
Has,
memorize these values?
what's that again? No, you don't have to memorize.
Okay, thank you.
Copper 2+ high has higher reduction potential. Basically means greedier for electrons. Okay, and this explains why when you set up a zinc and copper voltaic cell, the electrons spontaneously flew from the zinc half cell to the copper half cell. Okay. So, how did the scientists came up with these reduction potential values? How did they came up with these values? Okay. They used reduction of hydrogen as standard. Okay, the reduction potential of hydrogen is assigned a value of 0 volt. Copy. This image should, oops. This image should go here. Okay, so the reduction potential of hydrogen is assigned a value of 0 volt. Okay, and everything else is measured. Using hydrogen's reduction potential as a standard, as a baseline. Okay, and here's a diagram showing the voltaic cell using a standard hydrogen electrode, or SHE. Okay, you have zinc on the anode. Okay, and then so zinc is being oxidized, losing electron, its anode, right? And you have hydrogen on the cathode. So proton is receiving electrons that's passed from the zinc side, and it's being reduced and generate hydrogen gas. The arrow should be like this. Okay, it's generating hydrogen gas. It's being reduced. The voltmeter measures 0.76. If you stick a voltmeter here, it measures 0.76, which means that the cell potential is positive 0.76. This tells us that cell potential is positive 0.76. Since we know that the reduction potential of hydrogen is given a value of 0 volt, we use cell potential value of positive 0.76, and we use reduction potential of hydrogen, a proton, which is 0, right? So we use these two values to find out the reduction potential of zinc. And this is how all other reduction potentials were found, using hydrogen as a reduction of hydrogen as a standard. So the self potential can be found through this equation. Reduction potential at the cathode minus reduction potential at the anode. So if we want to find the reduction potential of the zinc, here, we wanted to find the reduction potential of the zinc, right? We need to rearrange this equation, find the unknown reduction potential at the anode, okay? Or of the zinc equals to reduction potential at the cathode, which is basically protons reduction potential, okay, minus cell potential. So we know that this value, scientists assigned a value of 0. Okay, and then the cell potential was measured from the voltmeter to be 0.76. So then the reduction potential of zinc is minus 0.76 volts. And let's go back to the table, see if this is the right value. Okay, so the reduction potential of zinc is negative 0.76. This is how table 20.1, the reduction potential table, that table is tabulated. This is how reduction potentials of all other substances were measured by using hydrogen's reduction potential as a standard. Okay. Another thing to note is that cell potential here, this is an intensive property. Okay, this is an electrical potential, measures potential energy per electrical charge. Remember, the unit for this is joule per coulomb. Energy per charge. Okay, if we increase the amount of substance in a redox reaction, we increase both energy and both charge. Okay, so the ratio of energy and charge remains constant even if we increase the amount of substance at the redox reaction. So changing the stoichiometric coefficient in a half reaction does not really affect the value of standard reduction potential. Okay, so that basically means that if you were finding reduction potential of 5 mole of zinc 2 plus versus 1 mole of zinc 2 plus, the reduction potential is going to be negative 76 volts. Okay, so the cell potential and the reduction potential, they will not be affected by the stoichiometric coefficient. Okay, and then so if we were to use the standard cell potential equation to find the cell potential of copper and zinc voltaic cell, since according to table 20.1, the reduction potential of copper is positive 0.37 volt, and then the reduction potential of zinc is negative 0.76 volt according to that the table. According to table 20.1, then using this equation, we can find the cell potential of the zinc copper voltaic cell. The zinc copper voltaic cell potential is going to be reduction potential at the anode minus reduction potential at the cathode. So you have cell potential of positive 1.1 volt. And again, due to a more positive reduction potential value of copper, if copper and zinc were to make a voltaic cell, copper is more likely to become reduced, and zinc is less likely to become reduced, or zinc will be oxidized. Zinc will lose the electron war to copper. Okay, so the cell potential is basically reduction potential difference between copper and zinc. Reduction potential between copper and zinc. Okay, again, cell potential and cell potential the value has to be positive. The difference between two reduction potential at the anode and cathode has to be positive in order for electrons to flow spontaneously from one direction to the other. Make the voltaic cell operate properly. Okay, I'm going to write that note down here. Has to be positive in order for the electrons to flow spontaneously from one direction to the other direction, to the other, okay? This will make multi-cell operate properly, right? Because if there's no continuous flow of electron, there will be no electricity generated, right? I have to stop the lecture here today. I have to go somewhere. So that's the end for today's lecture, and I don't have time to stay longer for questions. So if you have any questions, please send me an email, or I'll see you guys on Thursday, and I will finish